Hello and welcome to our stiffer C-feeder tray attachment method video. I am Logan Stewart and I'm here along with Chris Laser and Jay Fry.
So to start, let's talk about the need and problem statements. The customer need is straightforward. ERIES requires a solution for C-feeder trays whose torsional and natural frequency fall too close to the drive's operating frequency. When the frequency ratio approaches 1, the system risks resonance, which as shown in the graph to the right, causes the vibration amplitude to spike dramatically, potentially damaging the feeder and producing inconsistent material flow. The problem is that because the tray frame geometries vary, depending on the feeder, certain tray configurations end up with natural frequencies near that dangerous resonant peak. Each case requires individual engineering attention, which drives up labor costs and redesign time. The graph to the right illustrates exactly why this matters. Each curve represents a different dampening level. Notice how near a frequency ratio of 1, even a small shift in the system's characteristic causes a massive change in amplification. Our goal is to push natural frequencies high enough that operating point stays well to the left of that peak, safely away from resonance.
The Model C feeder is an electromagnetic drive system. It uses an alternating current system to move particles or material to a specified place in a smooth but linear way. There are no belts or rotating parts, which is very important because it allows for little to no downtime due to maintenance. There aren't really any parts on the system that can wear out over time with use either. Some things to point out on the picture to the right is the rear and front spring stacks. These springs are small sheet springs that are used to tune the feeder, in this case to 60 Hz. The tray itself is a large red piece on top of the blue drive. As shown in the animations below, the material moves in a smooth, linear consistency down the tray attached to the drive. The vibration is excited by using magnets inside of the drive that flip their polarity. This flip is what keeps the vibration smooth, thus allowing proper material flow. These are the 4 tray designs that ERIES has given our group to find a common error and fix. As you can see, these modes are all torsional modes and they all exist right around that 60 Hz. This showed our team that the failure mode in the case of these trays all appear to be due to twisting shapes. This gave us a focus point to then design a system to help drive that natural frequency range away from 60 Hz.
As previously discussed, the primary issue identified in the original designs was that torsional modes were the main contributor to resonance. These modes occurred near the operating frequency, leading to unwanted twisting behavior. To address this, we introduced square tubing along the length of the tray. Because this tubing is a closed cross-section, it significantly improves torsional resistance compared to the original open geometry. This added stiffness helps reduce twisting and improves the overall dynamic behavior of the system. Looking at the model impact, we see an increase in natural frequency of approximately 12 to 15%, while the mass change remains minimal within about positive to negative 5% of its original mass. It's important to note that these values are averages across all 4 problem trays, showing that the design is not only effective but also consistent across different configurations. The placement of the square tubing was based on regions of high stress and large deformation, ensuring that the added material contributes as efficiently as possible to stiffness. From a dynamic perspective, the natural frequency is governed by the torsional rigidity, which is the product of the shear modulus and the torsional constant, divided by the mass moment of inertia. Since the material properties and mass remain nearly constant, the increase in natural frequency is primarily driven by the increase in the torsional constant, J. As shown here, the addition of the square tubing significantly increases the torsional constant compared to the original geometry, leading to a corresponding increase in torsional rigidity. Overall, this results in a higher natural frequency and effectively shifts the system away from resonance.
So now that we've walked through the engineering behind the square tubing solution, let's talk about why this design is practical to implement. First, it's easy to implement. The labor requirements are manageable. Square tubing is a standard, widely available material that's cost effective to cut and weld into existing trays. No special tooling, no exotic materials, no major changes to the existing manufacturing process. Second, it's extremely cost effective. Breaking it down across our 4 tray designs, the total cost per tray, including material, cutting labor and welding labor ranges from about $70 to $106, with the average of all of them being just about $120. For the engineering improvement this delivers, that is a very low price to pay. And the engineering improvement is the most important part. By adding this square tubing, we have increased the tray's torsional natural frequencies by 12 to 15%. That directly solves the core problem we identified at the start of this video. By pushing those natural frequencies higher and further away from the operating frequencies, we keep the frequency ratio well below 1, and as we saw on that response curve, staying away from the peaks means no destructive resonance, consistent vibration behavior, and predictable performance across every single tray design. So to summarize, this design is simple to fabricate, affordable to implement, and most importantly, it works. It gives ears the standardized, reliable tray frame performance they need across all applicable C-feeder trays.